Okay, everybody, good afternoon. We have one talk today, one talk tomorrow also at the same time. Today is going to be Jinchao Xu, who is going to talk to us about deep neural networks and multigrid methods. Please.
Thank you very much for giving me this chance to talk. I'm new in this business, so I just want to talk some kind of some of the thoughts I've done recently. Usually when I remember in the old days we're talking about there's three different approaches to do science: experiment, theory, and computational science. Now you have something called data science. One of the questions we often have is data science really a science? I don't know what's the definition of science, but if you have some methodology to get the job done, I have the analogy I called, English is my second language, my native language is Chinese. I have two different ways of studying these different languages. I use a theoretical approach to study English, grammars, structures, and but my native language is no theory. It's all data, all practice. So I speak better Chinese than English still. So, so the question is, what kind of mathematics we can talk about the data science? So I first learned this word deep learning like 3 years ago when I had dinner with Bin Yu from Penn State. She was telling me this thing called deep neural network, deep learning. So she explained a few things which I couldn't quite follow. That I went to check the wiki. And it's deep neural network is really, the deep really is called multi-layer networks, different layers. And neural is called for neuroscience study. From a mathematical point of view, you can probably drop that word. I'm going to do multigrid. Then I say it, multigrid is multi-level grids. So literally the same thing. so then I got curious, and so start to dig in. And today I'm going to report some of my kind of exercise I've done. Let's talk about finite element. So some kind of, I don't know how many of you, let's just very quickly, I've been spending the last 30-some years just doing this simple problem, solving X equal to B mostly. And it still is in most of the computation, it takes a lot of time. It's still the most commonly used method is still Gauss elimination. Well, everybody knows this. Now the question here is that is the cost, of course. I don't know if anyone knows, it's the fastest computer still studying. 1 million unknowns, how much time it takes? According to the report, it's about 2 seconds. But if this is, don't take this number too seriously. The error can be 100%, but still makes sense. But if you do 1,000 times, that's about now, 100 times 22 days, a billion would be like 60 years. So simple math problem takes time to solve. So again, now we're going to do iterative method. Since machine learning these days, you can do all kinds of iterative methods. I'm going to take this, what people like to say, the gradient descent method. You take the gradient descent, negative gradient direction, this is pretty much, when you do this particular problem, I'm going to assume it is a definite, for example, to begin with. You can do a diagonal scaling precondition. If you do a more general case recently, if you use something like a Bregman distance or things like that, it can be associated with some kind of precondition or stuff like that. But anyway, this is like a Jacobi method. And we know this one's converges. So this is my kind of favorite example to get warmed up. But you take a 3 by 3 matrix, and so let's say this is a semi-definite symmetric problem. It has two positive eigenvalues, zero eigenvalues. There's 1, 0 eigenvectors. This is also in the range. My question is that I do gradient descent math. I iterate. I do a perturbation. If you take epsilon equal to 1, that's like a very good symmetric positive definite problems. So I can tell you the number of iterations is 37. Now I'm going to decrease it. So it's going to go up or go down. It's getting more. Get more singular. So this is that it's kind of annoying that for this simple little problem, this gradient descent method can be so slow converging. It's one of the problems of the major problem of machine learning, but also in scientific computing in general. Now we'll take a singular case. So in this case, you can still do gradient descent method. You can form it. And I'm going to take the right-hand side in the range. So this problem still has solution. Every two solutions differ by multiple of these things in the kernel. So it's still, another question, does it converge? So I spend quite a bit of time on these problems, but the result is kind of a surprise, at least was surprising to me. It's convergent very fast. And the question is why and how do you actually fix it? That's all. Actually, this little couple of pages summarize many of the things I've done over the years. But this is just an oversimplified example. But it still kind of speak to the key issues of some of the problems. Now the question is, how do we fix these problems? That would be. And let's try to provide a fix of this problem. If you do this, we can say this is the basis function, basis vectors in R3 to do the expansion is unique. But I'm going to add this constant vector, I have a 4 vector. I do the expansion for 3 vector. We all know from linear algebra this is not unique because they're linearly dependent, right? But nevertheless, you can also do the expansion. So you can also see that this P is on 2, right? So the P transpose will be 1 to 1. So if epsilon is positive, let's say, this even in general is also okay. These two system equations are equivalent. Except that this problem that the solution is not unique. Okay, because the representation is not unique. But I told you I don't mind about non-uniqueness. But after you get an x tilde, you can time px tilde, you get uniqueness. So now let's do a gradient descent, but this time I do a diagonal scaling, okay, because of this unbalanced diagonal. So the things I can tell you is that the number of iterations remains uniform, constant. So this phenomena is actually quite generic. You can make it with, I've written many papers over the years. But I also try to explain this for the multigrid method. Let's try to, I thought this one is something to think about it, but it is not by luck or special. There's some general principle behind it. And we're going to use the second. Now this, how many of you have not seen finite element? I have not seen finite element. Oh. No, raise your hand. Okay. So I can do fast. I beg your pardon. Okay, you do a. But I probably spend more time to do data, machine learning stuff. You do the variational formula, you do the piecewise linear functions, you do all this stuff. So you get, this is a piecewise linear function. So you do the basis functions, as you all have seen it. So we have this linear system equation. Okay. So what's new here? What's new here is I'm going to write this as using machine learning language. Okay. So this is something called the convolution in this neural network business. So you have this one D, you have this kernel, you do the convolution. Basically, you do a linear operation locally at point I. You do this operation locally. Every point remains the same. So I'm going to write the linear system equation as a convolution. So this is really the final different stencil. Okay. So that's the thing I'm trying to relate. Then you can know the 1D is already interesting because you do natural language processing. You have the sound waves, you know, these curves. You want to do propagation and stuff. But in 2D, it's an image. I mean, if you have an image, I consider an image is a two-dimensional function. So in this case, I'm going to think about my Poisson equation. So the Poisson equation, you do find the element of finite difference. You get this 5-point stencil. Again, I have a kernel, which I call this one kernel in this machine learning language. Is you do the convolution. So that's the equation we're trying to solve. How do you solve it? Multigrid. So in it's like a 3x3, 4x4 case. I have this 7-11 game here. So you have you think about do the 1D problem, it should be 7x7 matrix. That's another basis. But you want to put this all the 2 bases, 4 bases, 3 bases function cos grid into it. These are linearly dependent. This 11 functions. But you multi-D you can do linearly. Now, so this is what we call a frame. You use wavelets, sometimes use this terminology. So it's like I do the expansion for this 4 vector, the 4 vectors. But here I do 11 basis functions. Oh, it's not a basis function. So linearly dependent. I do the expansion. So I got an 11 by 11 matrix. Instead of, okay, if you do this one here, because this is divided by one of the edge here, that's why you don't get this. So you either do this 7x7 matrix, that's the standard stiffness matrix, or you do the 11 by 11 matrix. You put the other 3 basis functions into it, 3 functions. Now you do let's do 2D because then you do, so you get an idea. So you do the standard kind of stiffness matrix. Here you do the expanded kind of frames. Now you do the gradient descent method for both of them. This is like 3x3. This is like 4x4 in my simple examples. We all know that if you do gradient descent, this takes forever to converge. But this one, the number of iterations remains constant. This is a multigrid method. It's a kind of multigrid method is pretty simply that you can think about it. You have to go visit all these course spaces. But I want to, this is a quick way of doing the multigrid, but the way a multigrid you can do is that one of the things like smoother, I'm going to present an equivalent mathematical formula which takes a little bit more time to explain, but at least I gave you some idea. Multigrid, there's something called multigrid that works very well, but I make a more kind of equivalent formulation. This is based on some kind of smoother, which is simple iterative method. This one, maybe you can just say gradient descent method. But if you do the gradient descent twice, I want to use this convolutional notation. If you do it twice, it's still a kind of a convolution. This is like a Jacobi or the gradient descent method. I use gradient descent as a smoother, and then you have this iteration method like this. Another ingredient is there's a prolongation restriction. The prolongation restriction turns out in the machine learning language you call pooling. You do, but here I do the restriction is really the this is for this piece of linear function. You have this kernel, this kind of convolution with stride 2. You just go to the coarse grid point. Anyway, so you've seen I'm just trying to write the multigrid algorithm in terms of machine learning language. Now, in my class right now, I teach. I ask students using this Python, no, the PyTorch or TensorFlow, because it's very easy to write a multigrid algorithm there. If you, I talk about geometric multigrid on the uniform grid. So if you do this, the multigrid method in this more recursive kind of way, not the kind of expand the system, the 11 matrix. If you do it, you can do an initial guess to a random initial guess. So, in this machine learning, they always want, it's important to random initialization, but okay, I put a random here, but it doesn't matter. So the G is the right-hand side. You can think it's a graph or EEG. But anyway, do the smoothing. Smoothing is just some kind of simple iteration. As I said, that you can do a Jacobi or Gauss, you can do a gradient descent method. So it's some kind of kernel. And then you form the residual, you do the restriction or do the pooling to the coarse grid, then you repeat the process. But that's pretty much the multigrid algorithm. You can also do prolongation restriction, but the convolutional neural network, as most people use, Yang account, what he just do the fine grid of the course. They don't go back. This is what we call auto encoding and decoding. But anyway, I just do one branch of it, maybe in this talk. It's called a slash cycle. So multigrid is just extremely efficient if you do this exercise I did. Of course, this is a very simple problem where it's a generic problem. We're talking about on summit, I don't know how many millions of core there. Multigrid on, I take 1/4 of this computer, and you do this, you go to 1/4 second. But this scales linearly. If you do these things, you do one core, there's a few millions core. This day and night different. Talking about only 4 minutes or 1 billion unknowns. You can do very complicated problems. This multigrid efficiency is phenomenal. Now the question is that multigrid, okay, it's powerful when it can apply. Sometimes it's difficult to get it work. But the question, can the power of multigrid be transformed to machine learning? Is my question. This actually has the CNN structures, and actually, I'm actually was thinking about originally. I was trying to speed up the training algorithm, because the training algorithm is a gradient descent method. You can think of like a smoother in multigrid. So now I think I know a few things about multigrid. I can probably speed that one up. That usually takes a few days to converge. Millions and millions of iterations. And but the thing is that it's like when I first got into this, then I said, okay, I don't know what problem I'm solving. So you have to think about the model. You have to know what problem you're solving. So that's my goal. But I'm actually doing CNN for multigrid for the CNN. I'm going to explain later. So this is kind of quick things about multigrid finite element. Now let's talk about what's the machine learning things. So one of the things you can talk about machine learning, you want to see how can machine tell the difference between these two species. But the way mathematically, I'm going to oversimplify things. I don't know if computer scientists maybe don't like what I say, but
before you go ahead, may I ask a question?
Yeah.
So I am not a multigrid expert, but I thought that multigrid wouldn't work on any kind of problem equally well. So for example, you showed us the Poisson equation, and that is very good for multigrid. But other problems will not.
Universal equation is okay, basically. Patrick, he can do Stokes equation. He can do precondition. and
So how do you know?
Maxwell equations. We actually did MHD. You have to work hard to get it right. Yeah, you're right. It's a.
So how do you know that in a sort of machine learning setting, it's going to be, you're going to apply
Right.
the method? Say that you're right, that there is an homology, right?
Yeah. I'm actually not talking about analogy. I'm talking about analogy in a very technical way, which I'm going to explain. This machine learning is a very wide subject, and I'm just trying to provide some partial understanding through the lens of multigrid. And the answer to your question is probably dependent. But at the end of the talk, actually, the big journal of actual numerical, I just wrote this paper called algebraic multigrid method. And that's in a way to answer your question in a more practical way.
Another way to phrase Elena's question, multigrid works for PDEs based on a certain structure of their spectrum. Why did the machine learning problems have that structure?
We'll see.
Probably not all of them, right? We have
Probably not.
Actually, the talk I'm giving today is to pose more questions and give answers. Something to think more about it. Okay. In the end, I'm going to draw a connection between the two different subjects in a very technical, specific way. It's not a philosophical connection. That's one of the things I want to say. And if you do these things here, how do you tell the difference between these three dog, cat, and rabbit? And you got to this is a matter of faith right now. If you take a 3 million pixel, you can think about let's forget about that. Maybe let's say just 3 million pixel, roughly speaking. It's just a vector, Euclidean space of 3 million dimensions. There's one point there. Now, by certain metric, okay, they should stick together. Otherwise, there's no way you can classify them. You can separate them. And so mathematically, it's a theorem I can prove. If you can do image classification, you can do something like that. Okay, but mathematically, you want to look for function. So this is called supervised learning. Okay, so if cat I call it 1 0 0, if the dog is 0 1 0, this is a rabbit. So I do a data fitting. I'm always simplifying. Actually, it's pretty much it. You do the data fitting. This is the 3 million vectors you put in there. Somehow you want to fit the data. Okay. So you have this is what is called training data. You have some picture. You have the label, which is 1 0 0 0 1 0 0 0 1. This 1 0 0 is not necessarily what they call a probability distribution. If you know for sure it's a cat, it's 1 0 0. When I walk in my neighborhood, you see something looks like probably more like a cat than a dog. This hybrid. Even the label is probability kind of thing. So with high probability, it is a cat, for example. So you want to find a function so that this one equal to say you just do the fitting, and the data fitting you can think about E square, but you can think about other things. It's a cross interview. I'm going to come back later on. Somehow you want to do the data fitting. Let's say E square. When you have a new photo comes in, a picture comes in, so as I evaluate this function. If it's a 0.8, 0.1, okay, it's a cat. So that's how machine learning AI, what they call these days, is being doing. I think this AI business these days, the core technology is image classification, and the very core of this thing is neural network. But anyway. So these are the more of the this machine learning is an old subject, at least maybe 50 years. Okay, let's do some math here. So what do we mean by classifying things? So then I have to think about if you think about go to the statistics, actually there always a linear regression. The linear function is already very powerful. Actually, lots of statistics. So you've given two sets, so I can use a linear function to separate them. This is called linearly separate. If you have two sets, you can put a hyperplane in between. This side is one set, the other side is one set. So the hyperplane is Wx plus b is a linear function. Less than 0, greater than 0. Now, it's interesting, how do you generalize this to multi-clusters? And you cannot quite just do it. It turns out, one way to, I still have not found the literature that's clearly spelled it out. I'm sure it's wrong, but the way to do it is that you find a k, if you have k classes, if I give me k different sets, I said they're separable. Linearly separable, what does that mean? The k linear function, so that this i1 evaluated at this sense I is bigger than this J's plane, this J's plane is evaluated by I. This is a bit awkward, but if you 2D in two cases that you can take the difference of the two together when I showed you earlier. Otherwise, you have some kind of polyhedrons to separate this very special polyhedrons to separate this sets. So this, I have a mathematical definition. Okay, something which is called linearly separable if there exists such a k linear functions that does the job in such a way. The question is that how do you find it? Okay. This is among things that this is what the logistic regression is doing. So what you do is that there's something called softmax here. You raise the exponential power. Now you make this k linear function into a probability distribution. Okay, and if this one is bigger than this one, you still exponential is a monotone function, so you still preserve the order. Okay, or the monotonicity. So this is a probability distribution. So there's something called a likelihood function. You multiply all this together, and suppose it turns out if you do the maximal, actually in statistics they say the way to find this weight is maximize this likelihood functions. But usually this should be negative sign here. Sorry, you do some kind of you do the argmax, you do the argmean. Okay. You take the negative log is the argmean. This is called regularization terms. So you can prove a theorem. I still don't know. I proved the theorem. I don't believe it's new, but I asked many people. Statistics, people don't prove theorem like that. They just always have noise bias. Here I have the idealistic situation. I have the totally separable. Then I can say, if lambda is sufficiently small, if this one turns out this function is actually, believe it or not, this function is actually convex. This is the leg log. This is convex. This is actually a convex function, but it's not strictly convex. But you strictly convex, you don't really necessarily find the global minimum. And it's like 1 over x. You can never find the global minimum. And but if you do the regularization, if you are able to find the maximum value or the minimum value of this guy here, you can do the job. You can do the classification. You can separate the sets. Am I clear? You can find the k-planes to do the job I said earlier. But interesting enough is that if lambda equal to 0, you don't have a global minimum. In that case, it really looks like the function, this logistic function, the loss function is really. It really does look like a function like this. You can go to infinity, and you do not have a global minimum. In all this machine learning, you say, oh, let's find the argmean. And that's I until this day, after I studied this about off and on for 2 years, I still don't know what people are trying to minimize. I don't think anybody knows. They do the argmean, they can go from there. But if you need some regularization, and so if you want to do machine learning, at least we should do the linear case. This is my take of this. Okay. So you have this what they call this loss function. This would be a loss function. The interesting thing is that I don't have least square here. Forgive me. I don't use least square. In machine learning only. They actually use something cross entropy. It turns out this thing is the difference between two probability distribution, which is the labor and each one of these things, and you have this what I call K-row divergence. It turns out it is very much, I have very great difficult time to understand where this cross entropy come from. But if you look at the logistic regression, it actually comes from this negative logarithm, which cross entropy is considered to be very important in information science. The regularization is very important in machine learning. Even for this linear model, you may argue, is this a linear model or not, because you have exponential function. I think we should just call it a linear model. The exponential function is artificial things, and they just make it convenient. But it turns out this cross entropy, all that is kind of mathematically quite nice.
What's the R of theta?
Huh?
Still haven't figured out what R of theta is.
R theta, okay, good point. Let's go to the next page. This is regularization term. Okay. What other regularization should be used? We need a regularizer. Okay, let's do the what's called support vector machine. The logistic support vector machine again is widely studied algorithm in the statistics. So we took the two cases, binary classification of two sets. Now we say that this again, I mean, the idealized situation, this is perfectly separable. Now the question, I want to put a hyperplane in the middle. Where is the best place to put? Now there are some to have to keep in mind when we're doing machine learning. There's something called generalization accuracy. Generalization accuracy, if you have two sets here, there's A1, A2. If my plane is sitting here, it's too close to this one. Next time I have something kind of looks like in A2 class, but if you have a little bit of noise, if you go beyond it, it becomes A1. A dog, a rabbit becomes a cat. So you want to put the things in the middle. This is what a support vector machine do. You put the things in the middle. This is like the smallest distance to the largest, something like that. And if you do some elementary geometry, you rescale the things, this amounts to this. You kind of maximize the margin. SVM seems to be more reasonable. The logistic regression doesn't really tell you the quality of the separation. This one really tells you what's the best thing to do. Actually, this is for two cases, but if you go to multi-class, somehow still people have figured out. We recently have some results, which I was thinking of talking about, but I have so many pages here. But anyway, let's just get the idea. So in this case, so to come back to Douglas, your question here, so we actually recently proved the theorem. Again, it's probably in the literature. When you lambda, if you take the L2 norm of this Wx plus b, if you take the L2 norm of that guy, okay, that's the regularization term. But not the b. B is called a bias. Then you let the lambda go to 0. It turns out you found that this logistic regression, actually the solution converges to SVM solution. If you go to the you think, well, we have a lot of people doing finite element, but if you go to logistic regression, the Google, you get maybe 60 million hit or something. So many people doing this business. But most of the statistical book look at you have logistic regression, SVM. But when I was playing with this, oh my God, they must be related, but this is a relationship. So you can safely assume that these two methods are related, I think. Now, they are not obvious in the very beginning, though. But the thing is that now, this one, you certainly take into account the generalization accuracy seems to be a reasonable thing to do. Now, for the logistic regression, it doesn't address that issue. You need to introduce regularization. This would be one way to do it for binary classification. It turns out we actually have some theory recently that in the multi-class you can have some special form of regularization. But anyway, so you can do logistic regression. Usually in this case, this this constraint, you can do a soft constraint, formulate these things, but you can see they look very similar. But I guess what I'm trying to say is that if the set are linearly separable, then you can use both or either logistic regression or support vector machine to do the classification. Now, but in practice, this linear function, as you can imagine, linear function is not so flexible. Okay? But the amazing thing is that linear regression is used commonly in practice. But let's make sense of, okay, I say it's not linear separable. How about somebody is like a separable but not linear separable? What does that mean? I don't see people give the definition because when my presentation I want to give some definition. But again, I'm not going to claim like this has not been done before because I just cannot keep up with the machine learning like computer papers. But the way to do it is you find a long linear mapping. Okay, what I call feature map. So you map this set to a different space. Usually it's lower dimensional. Remember the classification, you have a 3 million pixels to come in, but the feature should be low dimensional, You just only be able to tell the difference. There's not much to ask actually, when you think about it. And I don't know how we human beings remember people, okay, this is Professor A, this is Professor B. So when I say that you need to find this long linear map so that the image are linearly separate. Does that make sense? For example, if you take these things here, this is certainly, you cannot put a hyperplane between these two. Okay. But still, you want to find the mapping. Let's take this is artificial examples. If you take this one, actually, I didn't have time to draw a good picture here, but in this case here, you have this thing, it's actually become a 1D problem. If you put in 2D, it's linearly separate. So you want to find our functions. So for machine learning, the question is what kind of function class we want to use. So if you have that function, so you remember before there, this is my logistic regression, logistic regression thing. You do the things here. In this case, I have other parameter theta. First of all, you have a linear model in the first place. So you do this long linear separable, you find the long linear function. I don't know what that one, that's the whole game, okay? So I put them together. So this will be, this is what they call a fully connected layer in machine learning. Fully connected layer is just, my interpretation is just logistic regression or SVM. So this is just a linear model, but this is a new data. Phi is the image of the original data. So now the question is what kind of nonlinear model you can take. I think I suppose everybody here probably agree, polynomial is always the most favorite thing to do. But the SVM has something amazing. Actually, I'm new in this business. They have this thing called a kernel method. And if you have the phi x and phi y, for example, and in practice, if you do the SVM doing this minimization problem, you actually find out that this loss function depends on the inner product of the data. I don't know who was the genius to deal with. Okay, I see the inner product, I replace by kernel. That's the kernel method. Okay. Okay. If you have these things in practice, you have xi dot xj, right? Xi dot xj is the inner product, right? That's in the code. You have this thing. I always simplify things. What did I do? So they just put a kernel here. In the code, you just add a k here. All of a sudden, the SVM do much better. And it's such an active research field. And if Gaussian, for example, you can choose. And but mathematically, if you do a Gaussian, you can actually prove there's such a phi. In this case, the phi maps into a higher dimension. higher dimension, if you make a lower dimensional thing to a higher dimension, more separable, you know, and more room to manipulate. Okay, I'm not here to talk about SVM, but the kernel method is a popular, is still active research field. I have 3 neighbors in my on street, 3 statisticians. Each one of them have this book of this big SVMs. All they're talking about doing with kernels. But here is one other functional class. That's kind of lucky, but there's also mathematical theory. It's very interesting actually. That's how to make this SVM so useful in practice. What are the other functional classes? And so again, this is our favorite function. What are you going to do?
May I ask a question?
Yes, please.
So what is this trick then? Do you understand why adding a kernel is just like choosing a different metric, or?
This book is 20 books like this big.
How to change an inner product?
I always ask that question to my statistical friends. Many people made a living out of it to do this kernel. One way they actually say that it's a kernel, there's a theory you can prove. For example, if it is symmetric, if it's non-negative, you can always find a function phi. It's an inner product. Gaussian, for example, can be written in infinite dimensional inner product. There's a theory like that. And so that we call a feature MF. If you go to they argue that if you go to higher dimension, it's more separate. Anyway, I know very little about it. I decided not to get into that because there's too many other things to do.
And you're trying to find a function phi that you can apply to the data.
Yeah.
So you start by choosing a Gaussian kernel and try to write it as a square.
No, you do linear regression, like what I did earlier. So you'll find that. Forgive me if any expert here. This is how I. The loss function depend on these things here. If you look at this realization, somebody at least put a K here just in the code. All of a sudden, everything.
What does it mean put a K there? The loss function depends on those things.
Yeah, the K would be just the this is inner product. You can do like a Gaussian kernel. You just change the inner product to some Gaussian kernel.
Where did you get an inner product? The loss function depends.
Yeah, but this is bit mathematics. Yeah. It's called representative theorem in statistics. It's a couple of lines proof in the right language. It's lots of quite a bit of mathematics in there, but I can't quite answer you. I ask the question all the time, but they have all kinds of many serious people work on it. What I'm doing here. Now the question is that these are the things we'll find the element I like spectral method waves. Now the question I have is why people don't use this. Okay, so this is the next pages. I'm sure most of you have seen. This is just special function class called a deep neural network, and
Yeah, you're almost.
wait a minute. What is the practical solution of this? Sorry.
If you forget about the time limit.
Yeah.
Oh, it's you can go. Let's say 8 minutes more. You can do 5 minutes over.
Okay.
It's okay.
Oh. So, wow, I got too excited. So you take this deep neural network kind of activation functions, and then you do. This is a linear function, then activation function. So that's half of the story. You do component-wise, you do the activation. Activation is a one-dimensional function. Then you do linear again, the activation linear again. So every time you do this such a thing called one layer. Otherwise, you have many layers called multi-layer. That's a special functional class. And the question is why this functional class is so interesting. So from the many people do approximation there. If this is like a one layer, you can do it this way. So ask the question: is this functional class rich enough? Is this one dense? You have a sigma, it's fixed. This is the name of the game, okay? Sigma is fixed. The weights change. Now the question is that under which condition this one is dense in continuous function class? I don't know if you have seen it, just you can stay quiet, but here otherwise it's kind of fun game. So what kind of sigma so that this one would be rich enough. How about a polynomial? Polynomial is always, they always say deep learning because of linearity. Okay, polynomial is nonlinear. Will this do the job? What do you think? So okay, take a fifth order polynomial, let's say, one variable function. If it's a fifth order polynomial, it's always fifth order polynomial. So out. This is times polynomial is helpless. Okay. Polynomial. The interesting question: what kind of function really does the job? Are you ready for the answer? This is what is actually a surprise. As long as it's not a polynomial, it's okay. I have no time, but there's a proof here. I skip. And you have to do approximation theorem. And the proof is very simple actually, but I shouldn't say that, but if you, yeah, it's true, okay. Well, it has to be a function, okay. I think the real statement is that it should be almost the number of discontinuous points is countable, almost everywhere continuous. Reno is the one which is the most commonly used. If you really think about it's piecewise linear, so I like Reno because it's piecewise, it's like finite depth. It's a piecewise linear functions. If you do whatever, if you plot it, you have crazy function look like this.
Where do you plot it?
This is a piecewise linear on these crazy shapes. This is each of the polygons is linear function.
So you're doing a 2D example.
2D, yeah. You multiply all the crazy looking, you can't even visualize a lot of polyhedrons. The question is that if I like this finite element better somehow. Now, why the world does this do a better job? The first question to ask is, can I use if I take any finite element, can I write this finite element as a deep neural network? This is the first project I give to. Yeah.
How should I interpret that thing on the left as a piecewise linear function?
Piecewise linear on each of these polyhedrons. It's not the finite element.
What do the colors mean?
Huh?
What do the colors mean?
Color is the boundary of the discontinuity of non-smooth. Oh no, the color, I don't know. The color means nothing. Sorry. I don't know why there's a color there. Very specialized piecewise linear function. Now this is a finite element. You have a grid, then you have a piecewise linear. Now the question is, can this be written as piecewise linear? As a neural network? So actually, I got this student working on this. Actually, Jinchao. So I have this student working on this. So he couldn't prove it, but it turns out he came back later. Okay, well, you cannot prove it. It's not true. For this one layer, I have this convergence. But if you do deeper, it's okay. If you do deeper, you can recover any finite element. Multigrid, since I don't have much time here. So I treat an image. I will do classification. I treat an image as a two-dimensional functions, like finite element functions. Now, okay, I can do my favorite example here. Now you ask me why this multigrid experiment. Here's my big assumption. G, I know G I solve for you. G is a graph image. U is what I call a feature. I made a big assumption here. There's a linear convolution things that I can do the job. There's a God-given A. For any given G, I can find a U. U would be my feature map. I can do the classification. Question is that what is A? I said God-given, but we use the data to train it. We just assume there's such an A, you just train it. And so I solve, I come back to solve this linear equation, except that U is used as a pixel. Pixel is non-negative. When you do a PDE, you do this iterative method, right? You solve this thing. When you do when you do a computation, you do the graph, you see a negative pixel, what do? You make it 0. It's like do the if concentration variable, the density, if somehow you cannot preserve. This is reloop. Huh? That's the reloop. This I call it this is kind of you kind of feature extraction. The feature, if you think about that, this is a high dimensional feature. This is like a U in some sense, but it's not. I just want to illustrate if you love which one you like. But it's a low dimensional things, but you want to. I use an iterative method to solve it. Now, if you think this is my multigrid method, right? This is a multigrid method I solve given GIF to U. So what is my called CNN? This is my punchline. Everything here is that. So only the red things here is what I add. I introduce some more channels, what they call. Whenever I do the computation, if I say a negative pixel, I make it 0. There are other things. The structure is identical, except some red stuff. Number 2, multigrid, everything is known. ASO known. Deep learning, everything is unknown. You have to train it. Why? It's not quite true, but the machine learning people make everything unknown. But I insist there's a lot of mathematical structure behind these things. Many things should be known. So what I'm trying to say is that multigrid is all given, CN is identical to the same. It's not a philosophical connection. What I'm saying is just mathematically the same. They all need to be trained. This renew in this case this is where this activation function comes in. Somehow it's just something, but I'm always simplify this about this rule of it. But there's something called channels which are important in this business. And in this color picture, you can think about 3 channels. And anyway, there's something which is CNN basically they train everything. Classical multigrid, they give everything a priori. So my proposal is that you have to compromise in both cases. And the CNN, you should not train everything, you should give some mathematics. Multigrid, you should not give everything. That's something maybe you need to be trained. But anyway, what I'm trying to say is I wrote some papers on this. There's several things I want to mention that using this framework, I can unify, I can actually get resonating, for example, is one of the most important variation of convolutional neural network. And we can actually derive this method mathematically. But anyway, the main game I'm trying to play is that now I have some multigrid, I know a few things. That's for mathematics. All of a sudden, multigrid is just, I insist my students should write a multigrid code first. They just make a few lines, change lines to write the CNN, the special CNN. So usually the number of parameters, for example, the 11 million for resonant 18. I just went to the code to make some changes. You can drop 3 million. But this is my conjecture should be, I don't know. My hope is that should be only 1,000 or 10,000. That's my dream. That's my conjecture. But anyway, again, we have, this local journal here, actually America. So the thing is that actually the reason I got into this, thanks to this paper I was asked to write. I spent 2 years working on this paper. So the geometrical multigrid, you do MgNet. We have this thing called algebraic multigrid method, which answers your question, they're more flexible. You can, for example, see it on graph. That people doing different multi-level training algorithm. That's all the things we can work on. Well, I know I'm running out of time. I do one final kind of. I don't know if I've watched some Chinese movie in the old days. You put your hands on your finger on it, like, oh, congratulations, you have a baby. Now the question is that this be widely believed it's been accurate in some community. If you talk about the medical doctor with scientific training. This is nonsense. And now I want to check the literature. There's no, scientific study whether this actual statement is true or not. So this is the first project I did. I actually got some. I'm playing golf. I got my golf friends, rich people. They're gonna go play to help me to collect some data, and so okay, we do ResNet and MgNet. I get an 85% of accuracy if you do the cross validation. Your binary classification that of AUC, which is some criteria they use. Well, I want to make the point here, the ResNet you need 232,000 weights. Here I only need 3,400 weights. It's like 67, it's about 70 times fewer number of degree of freedom, but I got a better accuracy. I want hopefully that this would apply. I was in Microsoft in June. They actually told me that this MgNet, this neural net with tens of billions, hundreds of billions of weights. What in the world you can train a neural network? But I thought if you do some mathematics, since you now can make a multigrid, right, there must be all this weights must be in just existing relationships. You don't have to train them all. Anyway, I'm sorry for the overtime, but anyway, I want to try to build the mathematics on the classical machine learning and I guess we end logistic regression. So I connect the multigrid and method, and ultimately my really goal is okay, most of our colleagues use machine learning to study numerical PDE or modeling. I'm using numerical PDE to do the machine learning. I'm a computer scientist. They're all smart, big people, which I don't know if I'm just mathematically. The main point is there's a few things you can prove, but I made a one-on-one relationship between a multigrid algorithm and a new neural network, which is you can consider a very special form of ResNet, which is also a special form of convolutional neural network. And again, this convolutional neural network is the core algorithm, the whole AI business. I would like to claim that. And so this is very core to the game. And so I think, again, I don't have answer to most of the questions, but I did bring up more questions here. Thank you very much.
Do you have a question?
So your multigrid, the multigrid algorithm is for solving linear systems.
Yeah.
And is there any theory of multigrid for nonlinear problems? Because of these sigmoids that you introduce in your algorithm.
Because of what do I introduce?
I mean, you say in order to make the analogy with the
the sigma.
you use the sigma, right? And this makes the algorithm nonlinear. And
Yeah,
this is not something usual in
Right,
multigrid for linear problems.
Yeah, this nonlinearity, as we said, is the one that saves everything. I somehow downplayed the critical role of it. It's the most critical element in this whole business. It's a long polynomial non-linearity. I have to add that one. Polynomial won't do the job. And yeah, this non-linearity. Then you're talking about this. Yeah, I just downplayed. I just trying to. Yeah, it's just not so clear why this works so well. But I'm actually not brave enough to answer that question. But I like to answer the question because I know a few things about multigrid. Can I actually to design my parameter, this weights W and B in an educated way, so that the number of weights can be significantly reduced. And because I know exactly, but by drawing these two connections, I kind of know what this machine learning people are doing. at least I have intuition because I know multigrid.
Okay, shall we